Okay, so given the time, we'll just dive right in. So Jennifer already went over this slide in her deck, but today we're going to focus on the bottom portion of it, as this is the part that ALCF has in their available resources for you, and that's the DataScale system and SambaFlow. And I've seen the questions about, how do we integrate or convert or bring our models to SambaNova, and that's how we're going to do that today. So what is SambaFlow? Our main support is for PyTorch at the moment. And what SambaFlow does is it acts as an interface between your PyTorch models and our platform. So it automatically extracts, optimizes, and maps compute graphs from Torch into data flow graphs on RDUs. And this lets you achieve a high performance without having to do low-level kernel tuning, as you usually do with, say, Torch, CUDA, and the GPU. It provides a consistent programming model. So whether or not you're using one RDU or you're using 30 nodes, it's the same programming interface. It does not change. The key parts, as you can see from the graph, are the SDK, which connects to the compiler, which is what actually takes your PyTorch model and converts it into something to be consumed by the RDU. And it also connects to the SambaNova runtime, which is actually the OS that runs the RDUs in the entire system connected to them. So we're going to dive in a bit into the compiler, a little bit of how it works, what it does, and what it provides you as a user. So this is sort of what the high level of the compiler looks like. You start at the top, which is where you are, your Torch, your model, your code. You come in via the PyTorch API, SambaFlow, and then that feeds into the compiler and the runtime. So what the compiler is a graph compiler that takes that graph from PyTorch of the model and converts it into a what we call a PEF, which is what is actually mapped onto an RDU. So the graph compiler, it takes a high-level graph and actually starts converting it into pieces that are consumable on the RDU. That's what our kernel-level compiler and kernel library do. So the kernel library, it contains the actual implementations of various PyTorch operators that can be applied to the RDU. And the compiler itself is what actually does the transformations and the optimization between the PyTorch model and the actual data flow graph. And just to sort of reiterate and make clear, the RDU is reconfigurable. So your model, when you give it to us, we actually map it onto silicon. So those PMUs, PCUs, the memory units, those all get mapped to be the structure of your model. So that's what this is doing here. This compiler is actually taking your model, its pieces, and making them mappable onto hardware, our RDU. And the runtime is what then will take your model and deploy it onto the RDUs. And it will coordinate the memory, it will coordinate the interface with the host, and it will coordinate all the training and memory operations that have to happen between all the RDUs. And that's all automatic. You don't have to actually set any of these things up. So you don't tell it to compile in a certain way. You don't tell it to hit this RDU or this runtime. It does that for you. Now the compiler does operate in various modes. Now, some of you might be familiar with, say, LLVM with compiler modes, and the idea is similar here. So we have an O0 mode, an O1, and an O3. And you'll see at the bottom of this slide, we have sort of graphical representations of what these modes do. So in O0 mode, this is usually used for the first bring up of a model. Every operator in the graph, so your Torch add, your Torch multiply, your Torch operations, those are all treated as single operators, and each one becomes its own function on the RDU. And you can see from the graph that that's what's happening. It's being chunked up into individual sections by operator. Not much optimization happens here. This is really just to get the model running as a first pass. It is not performant. It's very performance poor. So this is just to quickly test your model to make sure that it can compile and run on the RDU. The next level, O1, this is where we start actually optimizing the performance of the model on RDU. And we have what's called operator fusion. And we'll go into this in a little bit, in a couple slides. But what this fusion does is it takes your torch operators and fuses them into single units that can then be mapped as larger units onto the RDU. These fusion rules, there are several that are already predefined out of the box for you, but you can actually define your own. So if you have your own custom model with its own custom structures, you can define your own rules to tell us how to fuse your operators together, and then from there we can map them onto the RDU. This definition is done via YAML. So what's especially important about O1 is that it enables reusability. So in O0, every operator becomes its own section on the RDU. So there's not much reuse happening there. But with O1, the compiler will recognize fusion. So if it sees the same pattern in a graph, it will use the same fusion for that part of the graph. So it allows you to define rules that can be reused multiple times in your graph, which further increases efficiency, right? So since you only have one rule, you only need to map it one time onto RDU, is the idea. And that user-directed heuristics, those rules you can define, we call that O1HD. And that's where you define your own YAML file to apply these things. And then finally, we have O3. O3 works to optimize the entire graph at the same time. So the whole graph is a single section. This can work very well. It can lead to a very optimal model on RDU, but it's usually very specific to whatever config you're using for that model, right? You can't do much changes. Any changes to the model usually have to require a recompile because you're changing the whole thing at once. So on the one hand, it's very well optimized, maps very well to the RDU, but it's not as reusable, right? The structures don't enable that. So it's a trade-off, right? And we leave that to you to decide, right? Do you want O0, O1, or O3? It all depends on your model and your use case. And this is an example of a fusion, of an O1 operator fusion. So on the right, the blue box, that's our pattern. It's from Llama 2, and it's a self-attention projection, right? So you might be familiar with this. Starts with linear, has an add, then goes to power, mean, another add, root square, multiply, right? This is a very common pattern in a Llama model, right? This is repeated often. So what we've done is we've created a YAML file that captures this pattern, and that's the black box to the right of the blue box. And that's how you would define it, is that you would find the pattern, you would define your structure. So linear, add, RMS. You'll see that these things are all mapped directly to the structure in the graph you see here. And the heuristic, so that's the rule that tells the compiler what sort of optimization to apply, is a gem heuristic. We have a few built in, and you can define your own. And what this means is that this pattern can now be recognized by the compiler, and it can be used in multiple places. You don't just use it once. Anywhere that this pattern exists in your model, and leverage it. And of course, you can use different heuristics. You don't have to use safe gem. It depends on what the actual pattern is and what your model does. Brief pause. Any questions in the chat or any questions verbally?
There aren't any questions in the chat at this point, Craig.
Okay. Just want to take a check because I've been talking a lot. Okay, so moving on, a little bit more details about the heuristics. So as I said, each heuristic defines a different compiler strategy for optimization. These can get pretty in-depth, so they can involve how you actually tile your model on the RDU, how you shard things, how you handle parallel factors, and how you actually cut up the section. They don't have to get that low level, but there's a lot of sort of deeper fine tuning that can be done for our compiler. There are knobs to turn. But out of the box, we provide a heuristics for O3, so the whole model optimization. Also specific ones for patterns that are gem dominated, so that save gem you just saw, that falls under that. And we also have heuristics for MHA, so multi-headed attention. Because again, these are very common patterns in LLMs. So these heuristics cover many LLMs, so they're available to you. And as I said, they're plug and play. So if you want to use a gem or an MHA, they're available to you. And there are more variations coming. We are building more rules as we work with more models and find more patterns. And those become available to the users in time. Okay, so that's the compiler at a high level. Now we're going to dive a bit into the runtime. So this is the component of our stack that actually runs the RDUs. It's the low-level OS that runs the RDUs, the interfaces, the memory, the PCIe, and how that all interacts. It's built to be very high performance, very high throughput, and it's built to enable easy parallelization. So when we say that you can, just compile your model for 1 RDU or 30 RDUs, it's the runtime that helps manage all of that for you. So there's no need for you to get down to the level of CUDA and have to manage the memory and the allocations and where the kernels are going on which GPUs. You don't have to parallelize it yourself, is what we're doing here. So it supports high-level OSs. So we support Ubuntu and Red Hat. At A&L, we're running Ubuntu. And between runtimes, there are minor version backwards compatibility. So if you're in the 118 family of, say, SambaFlow, then you can stay within that family with minor revisions, and things will still work. And this slide, it's very dense, but we'll break it down here. What this is a sort of high-level picture of what the runtime looks like. So externally, you have your remote storage, any sort of external compute nodes, things that you plug into the DataScale system. And then within that, you have the nodes. So the host, which is the x86 that Jennifer mentioned. And this is where you actually plug in your apps. This is where you, as a user, comes into the DataScale. And the host is what runs the OS that enables the RDUs to run on the back end. And as you can see here, I'm not sure what that's for. That's all controlled and it's all connected via a single fabric. And what we enable with this is that within a node, you can do model parallel. So you can do model parallel across 8 RDUs. And then across multiple nodes, and even within a node, you can do data parallel. We do that via the RDU Connect fabric. This OS provides reliability, and availability, and serviceability. So the system, of course, we want it to be robust, we want it to stay up. So that's what that part of the fabric does. Of course, the Host Connect fabric supports external connections. So you can connect to, say, your NFS storage or to other compute nodes. Within the OS, we provide things like a debugger. We provide performance and system management tools. And wrapping that all up, we have what we call the SNML, SambaNova Management Layer, which is sort of a language agnostic interface that you can plug into to extract this information out of. So if you're looking at our the structure that we just saw on the previous slide, using that, we can provide multi-user and multi-tenancy support. So with multi-tenant, we provide that via OCI-compatible containers. So for example, on the SN30s at ALCF, we support singularity containers. And Jimmy and Darshan will talk about that a bit more later, those sorts of containers. And of course, multi-user. So when a user comes in and they deploy a job, they can deploy their job onto a single RDU. So when you apply for, you submit a job, and on ALCF SN30 that's done via Slurm, you get the full resources. So you say, my job needs one RDU. So your job will get that RDU to itself and all the memory associated with it. And then if others come in and request a single RDU, they can also run their applications on an RDU. And that's exclusive. So when you get the RDU, it's yours. The memory, the compute, communications, it's all devoted to your job on that RDU. Or of course, if you're running a multiple RDUs, your job takes 2 or 4, then those RDUs are devoted to just your job. They're isolated. And this is a sort of high-level view of data parallel on our systems. So this is within a node and across nodes and across racks. So it's ALCF, you have 4 racks, 2 nodes each. So that means that there are 8 nodes available to use. And our infrastructure, our data parallel setup, the OS, the compiler, lets you use those effectively transparently. You just compile your job and you tell it to be parallel, and that compile will produce a path that can be used on as few as 2 RDUs or as many as however many RDUs are available in your cluster. It's all the same to your application level. There are multiple topologies available, and which one gets used depends on the model and what's available in terms of resources. So you have all-to-all, you have hierarchical, all-reduce, multi-bidirectional ring, and various others. But those are decided on by the OS, right, the runtime. There is a highly optimized data plane that backs all of this. We call ours the Collective Communication Library, and it's purpose-built to handle communications between RDUs and between nodes. So it's meant to use that fabric very, very efficiently. And of course, as data parallel, we support all reduce, all gather, send, receive, what you would expect from a parallel operation. And we do support mixed precision, so IP32, BF16, in our reduce, rating grouping, sync overlap. And that's all handled automatically. If you look in the graph, you'll see that there's a call to MPI run, the MPI run -MP2 training app. So what that does is it effectively is just calling a test that's been compiled for parallel operations, and it will just deploy the job to the cluster, our system, and it will reserve 2 nodes or 2 RDUs and run the job. Other than telling your application to compile for more than 1 RDU, so compile for parallel, there's nothing more you have to do beyond that. Again, there's no need to tweak these settings to set these topologies. Just decide the number of RDUs, right? You just tell it what you want, and it works. And this is a little bit into our reliability, availability, serviceability. So we have hardware fault and error management, naturally. It's a managed database. So everything's recorded in that database, and it contains current and past events. And the way you interface with that database is via a tool called SNF-ADM. And what it can do at a high level is sort of output to you the current status of the system. It can tell you, if the RDUs are healthy. It can tell you if the PCIe fabric is healthy. It can tell you if there are any issues with connected storage, memory pool, and it gives you that all at a glance. And this is sort of a snippet of that at the bottom here, a little snippet of what's in the node. It tells you what's connected and how it's all, connected. And present and online is good. Present means that the OS has detected that particular part, and online means that it's running. If you see anything different, contact support will help you out. And then a little bit deeper into the application diagnostics and debugging. So, debuggability will provide at the sort of like the OS level. So we have something called Slurm Feeder, and this integrates with ALCF Slurm instances. And when you provide it a PEF file and the actual application code, what it will do is it will generate a batch script with all the necessary requirements to actually run that model on your Slurm cluster. So if you look at that bash script, you will see at all the minimum settings you need to run the model. So it will give you the batch size, it will give you the number of nodes needed, it will give you back, everything to tell you like what's needed to run this model. We also, of course, output things to standard out. So when you hit compile, when you hit run, we can print things out to standard out. So if you have print statements in your code, we'll send those out to standard out. And of course, we have our own metrics that we give output as well. So as compilers and runs are happening, we'll output those from SambaFlow. And we do record all of this. So within standard out also ends up in logs. So there are two important ones. There's the SN log and the SND log. So the SN log is where we output application information and graph information. So that's from your actual application run. That's where that information will end up. The SND log is where we output information from the SambaNova daemon. So that daemon is what is instantiated to run the runtime. So any issues with hardware will end up in the SND log. And those are both under var log SambaFlow runtime. And if you have issues, like there are errors, this is where support would ask you to go. They'd say, could you please give me the SND log from that run? And this is where you would find it. Observability. So if you're debugging, now how do you look into what's happening in your application? Well, you can raise exceptions, of course, in your program code. So, myself, I usually use PDB or debug.py. You can use those as well. Or you can just say, use exceptions, asserts, or print statements. Those will all be output into the logs and into the standard out. So whatever sort of flow you use can work with our SambaFlow stack. Diagnostics-wise, so actually diagnosing the system. We have three major tools that do this for you to see how the RDUs are behaving. You can use what's called the SN stat tool. And this will actually show you the RDUs in the node and show you what they're running. And it'll show you how idle and how much work they're doing. So you can see the actual statistics of your RDUs live. We have a memory stat tracker, SNDDR stat. So this shows you the health of the DDR. It shows you how much is being used, things of that nature. And then we have IO statistics. So we do monitor the PCIe fabric, and we expose that via the SN PCIe stat tool. So these three tools together will show you sort of maybe like a high to mid level, how the node is behaving and what it's doing. It can give you a sort of high level idea of the health of your system. The deeper details will be in the SN logs and the SND logs. And something that we'll be talking about later is SambaTune. This will be something that Kobe covers. And this is actually a tool to help you gain further insights into your model, so how your model's performing. That's what SambaTune is for. It's a pretty robust tool, does a lot for you. I think you'll all like to see it. And then to close it out, if you actually want to see more details on what I've discussed, it's all in our documentation. So the SambaFlow documents are available in the public. The link is here, so you can check the PDFs when they're shared with you. You can always ping SambaNova support via help@SambaNova.ai. And of course, you can go directly to the support portal, and there you'll find a means of opening up cases and tickets. You'll find our documentation again. You also find things like knowledge base articles to help you with your SambaNova journey. Okay, and that's all I have for this section.